construction of this particular natural number will show us that it's 85 digits. So it's a huge number, 85 digits. And again, you'll see in just a minute by the way we construct this number. What we're trying to do today is determine the remainder of this large number upon division by 6. So it's 85 digits, and again, you'll see that in just a moment. Now, y'all, what I'm going to do is I'm going to look at it like this. We want to think of this in terms of modular arithmetic, not necessary, but I like it. So we want to find out what n is congruent to, I'll call it r for remainder. And the notation here is mod 6. Okay, modulo 6. Now, y'all, if you divide any number by 6, that has to be a number between 0 and 5, an integer between 0 and 5. So we would have r is bounded below by 0, possible remainder if it's a multiple of 6, and above by 5. Okay. Okay, let's go and get busy here. All right, now y'all, this is the number, and you can see why it has 85 digits right here. If you just take a look here, 2 times 38, and I'll leave it to you guys to make sure I didn't make a mistake. It's 2 times 38 plus 9. Okay, and that's equal to this 85 you see right here. You get 38 because 47 minus 10 is actually 38 pairs. 2 times 38 is 76, and there's 9 more digits out front. So I got 85 digits. Now, not super important, but it is a large number. Okay, now a useful thing we can do right here is note that the n can be rewritten like this. The Hindu-Arabic expansion of this, it's digits times multiples of 10. And I put question mark there just because I didn't want to go to the trouble to figure out. You don't really need to know it. This last one is 10 squared, right? 46 is in the 10 thousandths. It's 10 thousandths, right? Or thousandths, I guess, right? So you would need 10 squared right there. 46 times 10 squared, then 47 is the last. And all these other powers, it's suffice it to say that question mark is just a member of the positive integers. I'll call that z plus. You can call it natural numbers if you want. Okay. So again, not important because there's an important result that says that 10 is congruent to 1 mod 3. That just means that 10 minus 1 is divisible by 3, and 9 is certainly divisible by 3. All right, and again, congruences can be treated much like regular equations. So it also follows that 10 raised to the n is congruent to 1 to the n, which is 1, okay? Now what happens here are in the congruence, notice we use congruence instead of equality right here. All of these powers of 10 are just equal to 1, you see. So again, this gets replaced by 1. This gets replaced by 1. All powers of 10 gets replaced by 1. And you get this statement right here. N is congruent to the sum of the first 47 natural numbers. Okay, modulo 3. Notice the modulo went in there, okay? Now, so again, this result, summing up the first 47 integers, this is known as triangular number. 47 times its successor divided by 2 is 24. Now this is congruent to 0 mod 3 right off the bat because 24 is just 3 times 8, right? So any multiple of 3 certainly leaves a remainder of 0 upon division by 3, right? So we get this statement right here, and that means that n is congruent to 0, and that's the same thing as saying n is a multiple of 3. So we know that much about n right now. N is a multiple of 3. All right, now, but also notice something that's super handy. N is also odd. Okay, that's clear, isn't it? N is odd because it ends, the last digit is an odd number. Okay, so the proof will be done once we prove this. We already know that n is a multiple of 3. Okay, if we can show that odd multiples of 3 are congruent to 3 modulo 6, that will complete the proof. All right, and this is a very straightforward proof. We can write 2k plus 1. That's the odd part. K is an integer, positive integer, I suppose, or non-negative maybe. 2k plus 1 times 3, right, is just equal to 6k, right, plus 3, right? But any multiple of 6 is congruent to 0 mod 6, since it leaves a remainder of 0 when you divide by 6, right? So this is congruent to 3, excuse me. This is congruent to 3 mod 6. And y'all, that completes the proof. Again, two things happen. We went to a little bit of trouble to show that n is a multiple of 3, but n is also an odd multiple of 3, 7 here. All right, and so we're done. Let me write this a little more clearly. Okay, QED. The two facts that proved it are n is a multiple of 3 and also showing that any odd multiple of 3 is congruent to 3 modulo 6. Okay, so if you want to, I'll just write it down up here. The remainder is 3. Finalize this thing. The remainder is 3. I think he observed the proof and didn't find any problem with that proof. Okay, the remainder is 3. He would shake or spin, I guess, if he disagreed. All right, that's all.